Hello, this is the video for the data structure and algorithms, and in this section I would like to explain about breadth first search. So in the previous lectures we already learned about depth first search or DFS, and this is the variant. Okay, so we learned already about the DFS. So this is another variant of the graph. We call it BFS. It is stand for breadth first search. So in this PowerPoint, we will learn about the concept of BFS, and we will learn the algorithm based on the Python code, and we will check about the properties of the BFS. Okay. So before we go to the BFS, I would like to explain more about the graph. There are more things that you need to understand about graph. So I include this one, some of the properties about the graph, like path graph. Okay, we can have path graph or linear graph. So it is a path with at least two vertices is connected and has two terminal vertices. So vertices that have degree 1. So we got terminal, terminal vertices. So here is the terminal and here is the terminal. So usually we can have this path graph or linear graph for like bus or subway. So this is the starting, again this is the ending. Okay. So the bus can have a route like this one, or yeah, the subway can have the route this one, and then it can return back like this one. Okay, so uh, this path graph is also another specific graph. Okay, so we can have these properties. The path graph is, it has two terminal vertices, so the vertices that have degree of 1, and then there is the other. Okay, the other vertices will have degree 2. Okay. So the terminal vertices, there are only 2, and then the other vertices will have degree 2. And we can also consider paths are often important in their role as subgraph. So the role in the subgraphs of other graph, in which case they are called paths in that graph. So this one, if we have this, yeah, we call this is also another path graph. So we can have the subgraph, and the subgraph of this path graph is another path graph. Bipartite graph. What is bipartite graph? In the industrial and management engineering, it is also important to understand about the bipartite graph. Bipartite graph or B graph is a graph whose vertices can be divided into two disjoint and independent sets U, V, such that every edge connects to a vertex in U and one in V. Okay. So let's say if I have U, this one, then the other I have V. Okay. So bipartite graph are used extensively in online space. For example, you want to search advertising, or you want to do like the e-commerce, and you want to find the similarity ranking. Then you may have like users and items. For example, one customer buy camera. Okay, so this customer A, B, C, D, E, and the item is the camera, or the other is like I don't know, like books, okay, or smartwatch, or tablet, PC. Okay, so yeah, then it is, if it is 5, the user A satisfied with the camera because it gave a high rating, 5. 1 means the user A does not satisfy with the book, and so on. So if it is 0, then the customer or the user has no experience with that product. So we can have this one as the B-part graph. So the users is the U, and then the items is V. And then we can have the connection like users and items, or the user A with item A, the rating is 5. The user A with the item B is the rating is 1. So something like this one. Okay. So using this bipartite graph, we can denote that as the U, comma V, comma E. So U is the set of the user, and V is the set of item, and E is the relationship between U and V. Okay, one. Okay, so we can also consider another kind of graph. We call it GSS, graph structure stack. So what is graph structure stack? It is a directed acyclic graph. Okay, what is this one? Directed graph. If you know the directed graph, we have the arrow. Okay, and acyclic. Acyclic means there is no cycle. Okay, no cycle. So acyclic means no cycle. So this directed acyclic graph is just only a direction without cycle, where its directed path represent a stack. Okay, how can we represent the stack here? So for example, we have this graph. So we can represent this as 4 stacks. The first stack is 7, 3, 1, 0. The second stack is 7, 4, 1, 0. The next stack is 7, 5, 2, 0. And then the other stacks, the last one is 8, 6, 2, 0. Okay, because this is the root. So we can make those kind of elements into the stack. Why this is important? Yeah, the one of the application of this one is the context-free grammar. So if we have one sentence, okay, so we need to check whether this sentence contains noun and verb. Okay, the noun is the adjective, and there is an adjective about the. And we have the noun consists of adjective and singular noun. This one, the little boy, and we have singular verb is ran, adverb is quickly. So this will build the sentence, and I want to know what is the. Okay, the is adjective, and then it is also a noun. So little is adjective, and it's also a noun, and it will be in the noun phase before we create the sentence. So these kind of things will be helpful for the like text mining. We can also do the traversing. So we want to combine, for example, we want to combine the graph and other data structure, for example, stack. Then in the previous chapter, we learned the graph traversing using BFS. So actually, if you still remember about the path finding, okay, the cycle finding, so we use the concept of stack. And the idea is, that one, we can combine the graph with stack. For example, we start the vertex S, okay, and then visit the first neighbor of S. What is the first neighbor? Let's say we have T, okay. Then visit neighbors of that neighbors, okay, and then we can have the V. Every time consider neighbors of the last vertex visited. So if we have this S visited, then we can S, okay, and then go to the next. Okay, we have T, and then go to the next. We have V, okay, and then we can visit this one U. Then you can have U. So it depends about the requirement. Then you can make this as the stack, and then after you know all those combination, for example, like this one, then I will check, okay, in order to reach X, then I can go to X, and then we will go from W, and then we will go from U, okay, and then, for example, V, yeah, we can just remove V because maybe the shortest path is from S directly to go to U, V, and X. Okay. So that kind of things you can define with your own code. And then you can also do with the Q. Okay. So if we are using the Q, it means we want to visit the first node, like for example S, and then we will visit the neighbor, okay, and then we will visit the neighbor, and then finally, yeah, we will exclude all those from the first node that we visited. So as you know that Q is first in, first out concept. So when we visit one node, and it will go out, and then we will visit U, then go next. V is then go next, W go next, and then X go next. Then we know that every node that we want to visit it is in this sequence. Okay. So yeah, the implementation can be anything for this traversal. So that's the many concept about the graph. Of course, there are many things more. If you want to learn more about the graph, you can take a look on other resources. But in this chapter, I would like to just limit on those concepts. And yeah, I would like to come into the breadth first search. Similar to the DFS, the breadth first search is a general technique for traversing. So the concept is traverse. And the BFS, similar to the DFS, it will visit all the vertices and edges and determine whether G is connected, and it computes the component, computes the connected component of G, and computes the spanning forest. So we can have the BFS with ON plus M. So we will check later about how the mechanism, how the BFS works, and we can use this BFS to solve other graph problem. For example, find the minimum number of edges between two vertices, and we can also find simple cycle. Okay. So now this is the algorithm. Okay. So we will take a look this one based on example. So I guess you are familiar with this BFS because it is similar to the DFS. We have the input graph, and then the output will be the labeling. So we will set U with unexplored, we will set E all with unexplored, and if every label is unexplored, we will run the BFS G, V. And then let's have BFS G, S. S is the variable for this algorithm. And then we will do this one during we visited every of the node, every of the vertex. Okay. The implementation in Python, you can take a look like this one. Okay. So maybe you will think that, oh, this is so, the complexity might be high. Okay. For example, if you take a look on this one, while, and then we have for, and then we have another for. Okay. So there are 3 for. So there will be like n power of 3. Yeah, basically, if you find the loop, you can just directly say this is the 1, 2, and 3. But usually we need to check about the while. The while, there are many concepts of while. So if the first while is if you have like the action equals to 1. Then it will be added every time you finish one statement. And then if, for example, the length, the while I is less than n, so it means you will work or you will do the operation until n, until the number of their data. So of course, in this case, this will be on. But the other kind of while, you can just check, like for example, while true. So if the condition is true, then you will directly execute this statement, and then you will loop every time before it is stopped. So here, the level, what is the level? Yeah, we want to find every time the graph is visited. So every time when you still have unexplored. So it means, yeah, it will go for every of the vertex or every of the vertices. And then for U in level, so the U is about the edges, and then, no, sorry, the U is the vertex, and then the E is the edges. Then for this one, yeah, it will not more than M, because I want to check only the M. So that's why we need to find out the details. If the component of the while is something like this, we can directly mention maybe the while is n, and then if it is also another n, then it can be n power of 2. But if it is not, then yeah, you need to check one by one how the algorithm works. So the idea is the same. We want to check the opposite, and then we want to check if it is not discovered, then we will set with discover, and then we will go to the next. So what is this one? Let's see. So the idea is the same with the previous DFS algorithm. Now we have unexplored, discovery. For this BFS, we use cross adds. Okay? In the DFS, we use back adds. It means if we return back to the visited node, then it is back. But cross adds if we cross in the same level. Okay? So what is level? So we will check later. Okay? Now we start from here. So we have A, and then we have B, and we have L0, and we have L1. What are they? Let's see. If we start with the A, okay, now you can take a look on this algorithm. L0. Okay, L0 is new empty sequence, and then L0 dot at last S. So because we start with the BFS G comma A, then this is the A. So set in the L0, there will be A. Okay, and then we set the label as visited. So let just me I write here. Oh, so I will write here A is visited. Okay, you know that all the other nodes are unexplored. So after you have this visited, let's start I with 0. Okay. So let me just put here I equals to 0. Okay. And then if not Li is empty. Okay, what is it? So it means if L0, okay, I is 0. If L0 is not empty, is it empty? A? Okay, that is A. Then it is not empty. Then we will go to this one. So you can see here, okay, based on the algorithm, we want to check the length. But basically, we want to check if it is empty or not. So if it is not empty, then you will go next. So there is no like repetition, what you learn about the repetition in the common for loop. So this is only to uh, do the repetition while the condition is true. Okay. So this line is only taking one time. And then we will make Li plus 1. So I is 0, then we will make L1. We will make L1. Maybe I will just put it in the, I will make this one more clear because visit it. And then I have L0. L0 is A. And then I will create L1. What is L1? The L1 is empty. Okay. Now we want to check for all V in the Li elements. What is I? So I is the Li. We have the V. The V starts with A. So we want to know all the elements. So it means we want to know first this is A. And then we want to find out the incident edges of A. What is the incident edges of A? Okay, we have the incident edges of A is B. Okay, so let's assume that we start from B. And then we will check. So we have the A to B. And is the label is unexplored? Yes, because we never been to B. So we would like to check the opposite of V. So the W is the opposite of A, comma E. Then we can get this one as P. Because it is P, we will check. P is unexplored. Yes, we never visited P. So set the label as discovery. And then set the label W is visited. Okay, then we will directly say this is visited. And then Li plus 1 at last W. Oh, this means I want to add the L1 with one element which is P. Okay. And then we will go to the next incident edges because this is the for loop. Okay. What is the next? Okay, after we cut this AB, then we will go to the next. Oh, we have C. Okay, so the next incident edges is C. So we will go to C and then check what is the C here. So if you go back here and then we will check, is there any incident edges? Yes. And then what about the label E is unexplored? Yes, because everything is not unexplored. We will check the opposite. So the opposite of A, comma E, now it is C. And then we want to check if the label C is unexplored. Yes, because we have no visited experience to C. So set the label E as discovery and then set the label W as visited. So we will make the C as visited. And then we will add the C into the L plus 1. So we have C. And then we will go to the next. Oops, this one. Okay, so we already finished with the A to B and A to C. Now we need to find the next incident. Okay, the next incident is to D. Okay, then let's explore D. We have the next incident, which is D, and then let's check whether the label E is unexplored here because we never been to D before. Okay, we will go next. we would like to find the W. So the W, this is the opposite of A, comma E. Now it is the D. Okay. And then we want to check if the label is unexplored. Oh yes, D is unexplored. So set the label as discovery, and then set the label D as visited. Okay. And then we will add the W. So the W is the D into the L plus 1. So we will add D. Okay, now we will go back again to the for loop. We want to check what is the for loop. Is there any other incident edges from A? No, there is no other incident edges of A. Then, because we have no incident edges, we will go back to this for loop. What is this for loop? For all element B in Li elements. Okay, so we have only A. What happened? Okay, we don't need to go to the other nodes because we have only A. Then we stop for this for loop. I will be added by 1. So now I, it is starting from 0, now it becomes 1. After we have I equals to 1, so we need to go back again to this while. What is Li now? Li is L1. L1 is empty? No, because we still have B, C, and D. And then we will create Li plus 1. So it means we will create L2 is empty. Okay. And then for all V in the Li elements. So for all V in the L1, we start with B, and then B, we will have the B, and then we will check the incident edges of B. What is the incident edges of B? So here, if you check on the data, so I will go next. The incident edges of B. So we have this incident edges. Okay, let's see. This is the first. So we will go to C. Okay, what happened if we check the incident edges to C? It is unexplored. Yes, okay, it is unexplored. And then what about the opposite of W? So I can just remove this one. So the opposite of the B is C. So the W, the opposite of B, comma E, is C. And is C unexplored? No, C has been visited. Then we cannot do this statement. We will set the label E as cross. Okay, so we will do the cross for the edges from B to C. So we make this one as cross. Okay, so you can see the edge from B to C is cross. And then we will check another edges. After we have the first edges to C, and then what is the other edges? We have the additional incident edges for B, and we go to the B. We go to the E. Okay, we go to this E, and then we want to check what is the incident. If it is the incident edges to E, if the label is unexplored, yes, that's true. So we want to find the opposite. So the opposite of this one, so we want to check the B, comma E, and the result is E. So I want to check if the label is unexplored. Yes, E is not visited. Then we will do the labeling for the E as discovery, and then we will do the set the E as visited, okay, and then add I plus 1 at last. So we will add this one with E. And then we go back to the incident edges of B. So is there any other edges from B? No, there is no other edges of B. Then we will go next to the remaining of elements. So because there is no other incident, so at the first we want to check the incident edges of B. Because B already set, finished, then we will go to the next element in the Li. What is the next element? We want to check C. Okay. So if we are now in the C, we will check what is the incident edges of C. Okay, the incident edges of C, maybe you will see the first one is this one. Okay, you will see this one. What happened if we choose that one? If the label is unexplored, we will go here. Okay. If it is not unexplored, we will set the cross. So it is already set as the cross. And then we will go to the next. We will go to the next one. We will find this one. Okay. What is this? This node to the E. Okay. Or maybe I will delete this one. So if the node, this one is C to the E. Okay, we will check. It is unexplored. Yeah. But yeah, if you can just check this one also, C to D and C to E. You know that E is visited and D is visited. So it means this one should be crossed and this one also should be crossed. Okay. So I will just skip the details, the remaining details. You know that everything, if the node has been visited, then it will be crossed, and then what happened? We will do the remaining incident edges to the F. What is F? Okay, F has been not visited. So we will just make this one as visited. So F is visited. And after F visited, then we will add this one in the L2. Okay. And after we put this one in the F as the L2, so we want to explore from the remaining, which is from the D. What about if we explore from the D? Yeah, because we already explored from the C. So we will explore from the D. What happened? Okay, in the D, we have only one edge and it goes toward F. And we know that F has been visited, so this will be also crossed. After we have this one, then everything already explored. Everything already set. Either it is crossed or discovered. Okay, so this discovered is the thick line, and then this dash line, dash line, dash line, dash line is the cross. Okay, then this is the final result from BFS algorithm. Okay. In order to check the BFS algorithm, we need to also understand properties. If you still remember, the DFS algorithm has two properties, but in the BFS, we have three properties. Okay. So the first property is the BFS visit all vertices and edges. And the property two is the discovery edges labeled by BFS form a spanning tree. Okay, so this is a spanning tree. So the same with the BFS, we can create the spanning tree. In the BFS, we have another property. So for each vertex in V, or it is in the level, okay, the path of TS from S to V has I edges. Okay, so if it is vertex in the V L0 from S to V has I edges. I is uh, the number of edges. Every path from S to V in GS has at least I edges. So for example, if I want to, uh, if you can check this one, in the first, in the L0, there is 0 edges. Okay, and then what about, yeah, this is the tree from S to V in L0. What about in L1? In L1, there will be at least one edges. Okay? There's at least one edges. There's at least one edges. So if we have like T, so T, because it is visited, then there will be at least one edges. Okay, so this property follows the BFS algorithm, but not the DFS, because it is different in the how the algorithm works. But according to the analysis, yeah, we have the setting and the getting. So we will check for every of the vertex, and we will check for every of the edges. So it will take O1 for setting and getting. And the same with the BFS, we will explore the each vertex twice. So we will set as unexplored and visited. What each of the edge is also labeled twice. We will label unexplored and discovery or cross. And each vertex is inserted once into a sequence Li. Method incidence edge is called one for each vertex. So you can see from the flow, so the incident edge will be called once, only one time for every vertex. It will not be executed more than one time. So the total time or the running time, we can say it is n plus m. If we use that algorithm, the result will be n plus m, provided the graph is represented by the adjacency list structure. So you need to understand the adjacency list structure in order to do this one, because if you use the adjacency list structure, you can optimize the operation time. And recall that the summation of the degree of the vertex equals to 2 multiplied by m. So some of the application of the BFS, yeah, using the template method patterns, we can specialize the BFS traversal of a graph G to solve the following problem in O n plus m. So for example, you want to compute the connected components of G, and then you want to compute the spanning forest of G, find the simple cycle. So this is, oh, maybe I need to put the simple cycle. Okay. So this is the application for a simple cycle finding. Okay. Find a simple cycle in G or report that G is a forest. So if you use the BFS, you can find the simple cycle. And then given two vertices of G, find a path in G between them with the minimum number of edges, or report that no such path exists. So this is a way to find a simple cycle, or you can find also the simple path. Okay. In the DFS, you can have path finding, you can have cycle finding, but in the BFS, you can just use one to find the cycle and also find the path. Okay. We need to compare whether DFS or BFS is good. Based on the application, the BFS and BFS can make spanning forest, it can create connected components, and it can find the paths and can find the cycles. However, yeah, for the BFS, it is good for the shortest path because the algorithm will check all the possibility. Okay, it will check all the possibility in the same level before we go to the next level. In the DFS, we will go toward the depth. So we go from A and then B, and then from B we will go to E. Okay, or for example, we go from A and then B, B and then C, C and then D, D and then F. Okay, and then because there is no further add, so we back to the E, D, and then back to the C, and then from C we will go to E. Okay. So we do not know whether it is the shortest or not with the DFS, but with the BFS, we can make sure that it is the shortest. However, with the DFS, it is possible to find the B connected components. So, for example, if you have forest, okay, like this one, if you cannot find any other, then you can have like this two. So it is easy to find with the DFS. And the other thing that you, if you still remember, in the DFS, we use backends. So W is an ancestor of V in the tree of the discovery edge. And the BFS, we use the cross edge. The cross edge means the W is the same level of V or in the next level. So there will be no possibility of the previous level. Okay, so the previous level will not be possible, but we can have it is in the same level or in the next level. Okay, so that's that kind of idea. You can try to find your own application in your team project, and I hope that it will be helpful for you to understand this concept. Okay. So, so I think that's all about the concept of PFS, and hopefully it will be easy for you to understand those two concepts. And I will continue all the things about this graph contents on the lecture next week. So thank you very much for listening. See you.